All right, got to get started. Hello everyone, welcome to this session on HBase in practice. I hope some of you came from like next door and have heard about what HBase 2 is going to add to its portfolio. There's lots of exciting things happening. I will connect to it wherever possible. But mostly this talk is about where does HBase fit into, or how to use HBase somewhere in an organization and what do you have to look out for. So just about me real quick, I was with Cloudera for a while, 5 years plus, and now running like my own company with friends. We founded a company all around Hadoop and big data and consulting and training around big data. And but I am doing Hadoop for much longer. Started with Hadoop in 2007. I am a HBase committer. I'm not really doing much committing lately because I'm doing more consulting. But I am still finding issues, logging JIRAs, and work on smaller JIRAs if I can. I'm also a Apache member and the author of the O'Reilly book for O'Reilly, the HBase, the definitive guide. I'm working on an update for those who know, some know me already. I'm working on an update. That's why the beard is that long. I promise not to shave until the book is done. So when you see me again and look like Catweasel or so, then something had gone really wrong. So hopefully next time you see me like in 2 or 3 months' time, that's done. So I'm finishing it off now, final touches. For today, the idea is we talk about sort of the brief concepts. I want to give you a bit of an overview because that's important. It's one of those things that to understand HBase and how to use it in practice, you need to have some concepts of how it works underneath the hood. And why this is important, we get into that. We'll talk about how you talk to HBase, then how you do the most important part, the most important aspect is the data modeling. How do you create structures that work well in practice with HBase? And then in the end, I will talk briefly about, this is like fairly short, but I think the sort of the culmination of everything. Where does HBase work well and what use cases you can use HBase well and which ones may not work as ideal, and wrapping things up then. All right, so from the very high level, if you just look at HBase, for those who haven't heard about HBase yet, from the very high level, HBase is just like a database. You have rows, you have columns where you can store data in. I always liken this to, say, like a spreadsheet. I say this is like, imagine Excel. You open up Excel with a spreadsheet, and you have columns and you have rows where you can put data in. So on a very high level, if I want to talk to a specific value, I need to know its row and its column, and then I can talk to its value. That's the same in a database. It's the same in spreadsheets. That's just our contract with this sort of tabular data. But if you really drill a little bit deeper, HBase is different. HBase is not like a normal database because it actually could be called schema-less, but none of the systems that call themselves schema-free or schema-less are actually schema-free or less, because they have a schema like document stores saying they're schema-free, but they use JSON as the schema, so it's like not really schema-free. So it's the same over here. We have a contract. The contract is that we have these sort of rows and we have columns, but you can have everyone separate. So here's an example where you have, for example, where we have 4 rows and they have different columns in each. And that is fine. That is something you can actually do, and it's something, one of those when we talk about HBase in practice, where does it work well? As soon as you have sparse or data sets that do not really have like a strong like schema of a relational type or of a normal schema that you know from databases, that was where HBase usually fits already from the start, from the get-go quite well, because you have freedom of choice of what you're doing per row, and you only have 2 real access points, which is we have a primary key, which is our row key. So the row key allows us to scan over what we need or find something specifically, take it out and talk to it. But we can also use those rows, the row keys, as our sorting mechanism. Only one direction. We can only sort ascending or descending. You can't even say ascending or descending. It's up to you to decide what the binary order is, because the binary order, it defines the sorting. We do a lexicographical sorting in HBase, which is byte by byte comparison between different keys. So if you want to have something descended sorting, you have to turn around the entire byte array when you store it into HBase, and then you get the descending sorting. So we only sort ascending, and that's it. And if you want to have something else, you have to change the keys to make that work. So instead of putting something in that is maybe like readable date or something, you would have to inverse this into something that is maybe not as readable, but then you get the sorting. We also get a secondary sorting within each row, and we can make use of this. If you look at this example here, you can see in the third row, each column actually has a timestamp as the column name. So this is one of those features where using HBase is quite nice, because you have the freedom of putting anything you want into those columns. And here we just have dates, like in this case, readable dates, could be just the epoch, like a long number that you can't read. But you can use this to sort the columns automatically. Remember back to this example of the spreadsheet. It's the same as if in Excel you go to the top of the spreadsheet, right-click on any column and say Insert. What happens? Everything gets shifted to the right, right? And you have a new column that you can put stuff in. We're all used to that. That's what HBase does for you. If you just have created a column A and F, and it's next to each other, like in Excel, and then if you say, I want to have a column B, which sits in between, HBase just shifts it out to the side and automatically makes this column B appear as if it would be had been there from the start and is between A, B, and then F is the next one. There are no empty columns because we don't need them. So all of that works quite well. In addition to that, we have a third dimension. That's the next sort of quality of HBase that in practice is useful. What you can do is you can have every value that you store in a table in a specific column and row coordinate, I guess, one of those points. Instead of thinking you have a single value there, like in a database. In a database, when you say update row 1, column A, then the previous value is probably gone unless you have a backup. Or in Excel, when you override something, it's gone, the previous value is lost. In HBase, this is different. In HBase, we have a time component. Every value has a timestamp, so you can actually override as many times as you want. Every override gets a timestamp, and if you want to, if you tell the system to retain a certain amount of these versions, then it does so. So it hangs on to, say, 3, 10, or 100, up to 2 billion versions. No one really goes that far, but you can go up to 2 billion versions in a specific row column coordinate and update values there. That's useful, for example, if you want to retain the last 10 passwords of a user, so that you can automatically say, or can go back and say, if he changes his password, or he has to change his password because of a policy, then you can say, what were his previous passwords, and check that he hasn't rotated the same passwords over and over, and things like this. And the API lets you actually, as I said, the API lets you talk to these 10 or whatever versions, how many you have given it. On top of that, we have the physical aspect of HBase. Now we are going one step larger. To really scale out, HBase automatically scales to any size that you want. There are clusters that we know of. They have more than 1,000 nodes. We know Pinterest, for example, has 1,200 nodes and 800 nodes of HBase. eBay has 700 node clusters. Yahoo 4 years ago already had like 1,100 nodes in the HBase cluster to store the web crawl. So I would say there are quite a few clusters out there, the 2,000 plus nodes, but not a lot of companies talk about this these days, but they used to do, and we know those numbers. So how do you scale to that size? How can you scale something to that sort of, to that many servers? The way that is done in HBase is there's an automatic chopping of data in 2 directions, horizontal and vertical. The first thing is we have the so-called regions. The regions are a set of rows in a table, and once you have a certain amount of rows in a table and they exceed a specific set maximum size, this is bytes really, just the actual size, then they get chopped into two new areas where you have one half in the top and one half in the bottom. And this keeps on going like this. As soon as you insert data into HBase, it chops the table into pieces, into the so-called regions. And these regions are distributed over the cluster, so there are nodes to host these regions. So your table is automatically, over time, distributed over all of the nodes in the cluster, and parts of your table are hosted somewhere, and that part has a set of rows inside that you can talk to. Finding where this is and whatever, you don't have to do anything, that's all taken care of, but that's how HBase scales implicitly for you in the back end. And the second option you have, you can also chop a region into halves or multiple pieces using column families. Column families allows you to group those. Remember I said a region is a set of rows. Rows can have, I don't know, as many columns as you want. to be able to have somehow disjunct settings on these columns, sometimes you also want to access them separately. That's where you use column families to do that. I get into that in a second. The only thing you have to do when you create a table is you have to specify a name for the default first column family. There has to be at least one column family. So it's one group of columns. So all of the columns that you create go into one column family with all the same settings and everything else. That's the only thing you have to do. The rest is all taken care of. There will be one region. As you insert data, they will split into 2, then 4, 8, whatever, how you insert data. And so the table is really just chopped, as I said, into those regions. They are really just connected to each other, so that when you look at the low-level settings of HBase, or there's a meta table that you can actually analyze, you will see that there's each region has a starting row and an end row, and the end row is really just the start row of the next region. We do this in HBase so that we can find holes. So we must not have holes in our regions. Therefore, the end key of a region is not in that region. It's just marked in that region. So if say the region goes from A to F, the F, the row that starts with F, is not in this region. It's actually in the next one, which starts with F. So we now know from A to F, from F to M, and so on and so forth. These are our regions, and we know there are no any gaps. You don't have to do anything. Everything is fine. Everything is healthy, and you can move on. But you just create your rows. As I said, you don't have to do anything. This happens behind the scenes. And there's a magic going on, like there's an assignment going on where these regions are moved into these different region servers. As you can have, like the smallest cluster would be probably like 3 workers. But the largest one, as I said, are more than 1,000, 2,000 nodes. And those host then the regions that then serve the data to the clients. The clients talk directly to those servers. There's a lookup mechanism going on, and that's done automatically, implicitly. You don't have to do anything. It's implemented in the client library. You just say, go to table A, give me row 1, and out of that one, give me the columns 1 to 1,000. And everything else happens behind the scenes. As I said, it's important that we use, initially when we talk about, again, HBase in practice is about giving you advice on what to plan for. This sort of column family notion is sometimes a bit hard to grok initially, because if you create a table and you give it you define your first column family, you give it a name like column family 1 or something. I see this quite often. You can store data in it. But when do you want to have multiple column families, and why? One thing is, for example, if you have complete disjunct access patterns to data. So for example, you get images and you do image recognition and you store metadata about the images, like when this image was taken, how many faces you have detected in that image, if you do face recognition, for example. So you have that heavier picture and you have this much smaller metadata. That, for example, you often just want to look at the metadata. Like once you have extracted everything you need from the photo, why go back and iterate over it? So you separate them in 2 families, and one for the picture and one for the metadata. And you can keep on going and do this and add more column families, for example, for specific different access patterns. But when it comes, like one part of, or one feature of the column families that is really interesting is that you have attributes that can be different per column family. For example, you can specify a different compression algorithm per column family. Imagine the image. The image is JPEG. Why would you want to repack or try to attempt to compress a JPEG image? It's already highly compressed. So that column family with the image, you just say no compression. Why? It's already compressed. That's fine. The meta one, which is quite verbose because you have like information in there that humans can read, you use a compression on that one, and so on and so forth. The other things you can set differently for column families would be how many versions you want to retain, or the time to live. You remember every value that we write into HBase has a timestamp. There's a TTL feature where you can say, if this value is older than a week, drop it. So they have an implicit delete of data without having to do anything. You don't have to go back and say, well, delete everything that is older than a week. You don't have to do this. You can specify this on the column family. But you might not want to do this for all of the values. So this is why you may want to separate out different columns into different families using these attributes of the column families to get different retention of data, different compression, different numbers of versions, and so on and so forth. So that's how you use that. And on the lowest level, these are really just directories on HDFS. So for those who know that like HBase mostly runs on HDFS, like all of the clusters I know of have HDFS as the backing store. You can run HBase also on other file systems like S3 and others, but in practice I have seen the majority of them, as my personal experience is 100% running on HDFS, not on any other file system. But in the end, what HBase does, it just stores these different column families in really just directories, separate directories on HDFS, so that when you ask for just data from one column family, it ignores the other directory. So all of the whatever data is residing in there is being ignored. How this is being done, like how HBase handles all of these like different directories, and where are the regions, and what's the start of that region, what is the end, what are the properties of the column families inside, and so on and so forth, is managed by 3 locations in HBase. It's the meta table. There are multiple catalog tables, but the HBase meta table is the primary one where we make lookups between user tables and regions on the servers. We have the HDFS directories, and we have the actual regions open on the region servers. And all of these are nicely aligned, but sometimes there is a fluke in the system, like a matrix effect. Sometimes things go wrong. So there might be, this is very rare these days, it was much more, it happened much more often in the past, but lucky that hopefully you're starting with HBase today. The occasions that you have to try to repair something is very rare these days, but there is a tool that comes with it. And remember when I mentioned that each region has sorted data, because it's lexicographically sorted, we have the start and the end key. We use this now to do these repairs. So what this HBase FS check tool does, it looks at HDFS, what are the directories, what's the start and end of all of the data inside of that directory, what's in meta, and what's in memory. And that gets now checked and then spits out and at the end a report saying something is inconsistent, and then you can start a repair. You can, for example, you can say, oh, meta was corrupted. Repair meta from what's on disk. Okay, that's fine. Say the disk is something happened to the disk, rare occasion, but could happen. Somebody's lost some files, like a directory is corrupted. Like something happened, someone deleted it, could happen. Then you can repair the other way around. You can say, take the meta information and create an empty directory with everything inside that is needed, and you're done. So all of that has to be done a few times. So in practice, again, because I'm talking about HBase in practice, that's very rare, but if you are ever in a pickle, there is a tool that you can use to repair the data in either of these locations. So this is all done with like, I think it probably has like 20 repair options for like meta repair, HFS repair, reassign regions that are not open and stuff like that. So now coming back out of this part, I'm diving into a different angle now. I'm diving into what HBase really is. If you ever want to think about what HBase really is, forget about that what I just said, like this whole table and rows and columns. HBase really is just a distributed hash map. Think about, you have a hash map, if you're a programmer, of those who are programmers, a hash map is, I have a key and I point to a value, that's it. Key pointing to a value, and that's all it ever is. The hash map, obviously, well, actually, hash map is not probably not the right term, it would probably be more a tree map, right, because it's sorted. So sorry for that. So it's a map, let's stick with this. And what we have is a complex key that points to a value. The complex key is now what you think, what you assume as a client or look at. The row key is, the column is, and this implicit timestamp, and a couple of other things I haven't like written down here. That forms a key, a dimension or like a coordinate in this space, and then all this points to is a single value. That's this value that we're looking for. Now you're also seeing, because of if you look at the left-hand side, you cannot have nulls. There is no chance of having a null. So if you had this sort of thinking of like a rational world where if you have defined a schema and a record has 10 columns and you have another record that only fills out 5 of those, then you have 5 that are empty and you have to put in some placeholders, the nulls in databases. We don't have that, because what you really have, you must have a value. Without a value, there is no entry. You can't even have a row in HBase with no value in the column. Because this whole concept of having a table with columns and rows stems from resolving this structure back into what looks like this. So that's exactly what's happening. And now this is important later on when we talk about how to do key design, because that compound key drives everything in HBase. Right? We get to that. Oh yeah, and the value here, when you ever refer to this, the actual concrete value pointed to by this complex key is called a cell. That's the lowest level that we have in HBase. The cell is the lowest structure that we have. That's the actual data. But the key is much more complex than what you think from the outside is. There's some internal stuff going on, and it has some overhead too. If you look at this now, if you look at V5, you look at this, the size. This is actually a string. This is 2 bytes. If you look at the key, there's quite a bit of overhead, because for every single value, we carry all of the coordinates. That becomes important later on when I talk about optimizing the system. What HBase does behind the scenes, it folds the whole, what you think the sort of like the table is, it folds this into these maps, into these sorted maps, then stores it out on file. And on file, you really have, if you dump a H file, so these are the files that HBase stores in HDFS, or in the file system behind HBase. Those H files are really just containing a sorted list of key values. That's it, straight as that. And they're separate, of course, per column family. So HBase is a column family grouped key value store at a different angle. The H file format, or the file that I just talked about, where all the key values are stored in, the cells, like the key with the cells, the actual data, they are separated usually by default in 64 kilobyte blocks. This 64 kilobyte block is a rough sort of setting. It checks that 64 kilobyte after every cell is being added to the file, which means if you, for example, store a 1 megabyte value in HBase, there is no 64K block in this file. There will be a 1 megabyte block with your data. So the minimum size of a block in HBase's files is what is 64. If you go over that, it will be larger than that. So that's something you have to also keep in mind, because if you want to optimize data on HBase for specific access patterns, for example, random access or throughput for scans, this block size might become important as well. So there's a trade-off setting this block size, how we index data in these files, versus how quickly we can access data versus how fast we can scan over it. We also only have the 64K block boundaries to find data in these files. So there's an index that is carried with these files, and this index tells us, oh, in this file there's a block that starts at A and it ends with M, and then another one that starts at Q and ends with Z, for example. And now the system has to figure out, if you're asking for a specific row, is this row or that column, is this in this block or not? And by default, as you used to have to load the block into memory, look inside and say, no, sorry, there's nothing in here, because you're asking for B. I have a block from A to M, but B is actually not in here. I don't know. And we added, quite some time ago, we added Bloom filters that help us to figure this out before we load the block. So there's some optimizations that are now default switched on as well. You already take advantage of this today, but there's some optimizations happening. All of these indexes, the index, the block index, and the Bloom filter, they're chopped into pieces as well, because we figured out after a while that if you create large files, these indexes and the filter can get quite large and unwieldy as well, using a lot of memory in the heap. We now have a staggered or multi-level or multi-layered index where we have only a root index in the file, and we load the blocks out of the H file, the partial blocks from the index or the block index or the Bloom filter on demand. So if we have to do a lookup of data and we need to fetch something out of a H file, the first time, we have to fetch 2 blocks out of the H file. So we have to fetch the partial index, and then we have to find the block and load the block. Next time around, this should be in cache, and then we don't have to do that extra lookup. But again, there's a slight overhead, but we can now scale much larger, and we can have larger files. Right. So again on the higher level, we have a fairly standard layout. We have a HBase architecture where we have a master and lots of workers. We have a couple of masters. You can have, for redundancy, you can start a couple of them, but we only have one active master and many, many region servers who do the actual workload. And inside we have components for writing, which is the mem store on the wall, and we have components for reading, which is like the region that reads from the H files underneath. So that's all done internally in this one, and we also use Zookeeper for orchestration. And if you really want to, that's the more complicated picture. I drew this a couple of years ago. It's still, I've updated this over time, but this is, don't look at all the details, don't squint your eyes. But this is, like I said, there's lots of moving parts, but it's all taken care of. You just talk to the table, right? This is fairly straightforward. It really is based on an idea that comes from its HBase is a truthful implementation of the Google Big Table architecture, and there's a technical paper that was released by Google calling Big Table, and this used some ideas that also date back before Big Table, like in the 90s, into what's called log-structured merge trees, which are used to convert all of the seeks that we usually have into streaming reads and writes, so that we make better use of spinning disk. That becomes a bit interesting, this fact, or this sort of approach with the SSD world we live in today, but it still holds quite true for specific features, even of the SSDs. For those who know, SSDs don't like small deletes, they also like to delete larger pages, and if we convert something into larger blocks that we read and write and also delete, that also the SSDs like this as well in terms of lifetime and things like this. But anyhow, so deletes are handled by tombstone markers. We heard this next door, for those who were there. We need to write to delete data because everything that we write on disk is considered immutable, so we need to update data even to delete data. So that's just the way it is. And atomicity is only done on the row level. We have facilities now to do this differently in HBase, but on the higher level, the only thing we can do is row level atomicity. And during reads, we have to redo all of that. We have to read the memory part, the disks part. Again, don't worry about this is all happening. But this shows you, for example, if over time you're writing into HBase, files are being created on disk, so data is being collected in memory and then written out to disk over time, we will have a number of files on disk that we need to look through if we are trying to recreate what you think that row is. So that row that you have updated over time might not be in a single file anymore, it might be in multiple files. And the more files we have, the slower our reads are, because we have to fetch blocks from I/O, we have to wait for these blocks to come in. Right, now let's have a quick look at how you can talk to HBase. You have the native client, we'll talk about this in a second. You have non-native clients, you can use a REST server or Thrift server in front of HBase. There are any JVM language can talk to it. Spark has a specific, again, if you were next door, as of HBase 2, we have officially Spark support in HBase, so you can have a Spark, either HBase context, or you can have a data frame that you can talk to HBase. So that's all done. And MapReduce is done for ages. You can use MapReduce in the Hadoop stack to talk and to read and write from and to HBase. We have a shell, a JRuby shell. It's sort of like for low-level stuff, but not really for productive use, where you can talk to HBase, create tables, and we have other tools like we also heard in the other room, Phoenix and Impala, Hive, SQL tools to talk to it. On the Java side, we have so-called CRUD API. CRUD stands for create, read, update, delete. And there are other variations of that acronym. The other one is crap, which is nice. So if you ever, when someone says that API is crap, then you say that's great, because I can talk to it, because you know what it is, right? So just saying, so this is from Wiki. Even you can see this, how this sort of maps to to the actual SQL world. In HBase, we have, in CRUD, we have a put, get, and delete. That's the entire CRUD. We also have some extensions. We can do a scan with like a cursor or so in databases. And we have increments, which do an atomic increment on the server side, which is nice. And we have some further extensions to that API, which is called CAS, atomic compare and swap operations, where you can say, fetch something from the server and only update it back onto the server if a specific field has changed. So that is possible too. You can also batch stuff together, and we have filters to optimize access patterns. Right. Now, talking about data modeling, that's now the interesting part. In HBase, the prime, and you remember now the map concept. In HBase, our primary access pattern is the key. And if you again remember what I just said on screen, you had that complex key. On the left-hand side in the key was the row key. So the row key is our primary access pattern, because if you do not have the row key, how can you go to a map and ask for something that occurs in that complex key at the second or third position? You can't. You have to scan the entire table to find all of the keys that have a specific value in the second position, like the column, for example, or another one in like the timestamp if you search for it. So the further you go from left to right in the key, the more you have to scan in HBase to find this. So the best access is always the row key. So if this sort of like summarize this, on left-hand side, the row key allows us to skip rows, to skip files, because we know this file doesn't have it, and so on and so forth. So that is the crucial part. If you ever design a table for HBase, try to design the row key clever enough so that when you, for your normal, the majority of your access to HBase, you know what you're talking to. If you have a use case where someone says, yeah, I have a key, it's just like the user ID or something, but I have to like find something or so that I have to, any user can have this. That raises already flags, which it might not be the best idea because you're doing a full table scan. So to really, for practice again, to do the right thing, you have to get the best performance in HBase. You have to know how to design the keys and the tables, because why do you need to know that? Remember, this is the same in databases. In databases, you also need to know, for example, that you have to create indexes on specific columns to do joins. So they're also exposing some of the implementation details to you. HBase is much more direct. It just tells you, okay, you have one major access pattern. Like you have to have the row key that you can talk to directly to a row, or you can scan sorted rows, and then that's all you can do. So you have to design a layout that matches you. And if you then ever say, well, but I have like 5 layouts for the same data. I want to access it this way and that way and also this way. Again, yellow flags. That's possible with like lookup tables, which you have to do on your own. But that might not be the best use case. HBase is optimized for one access pattern, and that's what you should use. And there's many use cases where this is enough, but there are also others that may not work that well. You may have to do things like you have to, if you had like previously you had like a normalized table, you may have to fold them together. Sometimes it's all possible to have lookup tables or small, like imagine like an order system where you have customers, orders, and order items. That could be a single row in HBase. So in a single row, which means if you need to find something of a specific user, you can go by user ID, you find the row, and you find all of his orders in this row. Go wider, and pack everything into a row if you need to. But there are other options. So DDI is this denormalization, duplication, and intelligent keys. The key design is your driving factor to get to have success with HBase. And then there are other things, like we often advise if someone's asking, so what should I do in HBase? For example, we advise that we say, prematerialize everything. Go ahead and, if you know that you need to read a specific, say, summary, for example, or a specific record, design so that you have the key in the front and you get all of its data out of that first. Don't do a join. Don't think that you can actually normalize and then at runtime you pull all of that together. If you do this at scale, this is going to be slow. That's just what it is. So we often find ourselves designing to build for reads, which means we prematerialize everything at write time. We take a hit because we have to write more data, but at read time everything is done, pre-computed, and we can pull it out as we need to. So design for reads is one of those prime ways of accessing, of designing for HBase. There are use cases obviously where reads are only secondary, you do mostly writes, and then you can optimize for writes too. But if you want to do lots of reads or specific reads, then you probably find yourself designing for it. Right. Then the other question often is tall and narrow or flat and wide tables. I often get asked, should I have a wide row or should I have rather a tall table and a very narrow row? That is sort of like depends. The critical part is that we cannot split those regions. That you remember, those regions are chopped rows, or rows are chopped up into regions distributed over the servers. We cannot do this at outside the row boundary. So if you have a very wide row, we have to carry that very wide row everywhere. So that's an overhead that you have to incur. And if you ask for the entire row, then this has to be pre-materialized and then gets batched to you through RPC, but it may just take quite some time and a lot of memory server side to do that. So often we find ourselves for especially data where you do inserts mostly, where we have very tall and narrow tables as opposed to flat and wide tables. So flat and wide is for entities, tall and narrow for scans and for like time series, for example, right? Just go to this. Now the sort of the takeaway of this one is, in HBase everything, and again, if you're at Ines' talk, everything's pluggable these days. This is just one pluggable subsystem. This is just one part of HBase, which I try to do to diagram somehow. So that everything you can tune. There's a lot of tuning options. This starts from the cell itself. As you heard, there will be an off-heap, an on-heap cell, and these things, sometimes you don't have to deal with it, but sometimes you have to. For example, compactions and caches. So for cluster tuning, what we find ourselves is often, first we tune the cluster, where we have tuned the settings, heap size, garbage collection settings, the memory share for reads and writes. We have to enable the block cache and configure it. Have to tune the RPC stack, set the handlers higher because the default typically under load is not enough. Tune the load balancer. So these are some of the settings are cluster-wide, which means you have to decide if you actually tune them or not, because they might have an effect on all of your users. And then we go down and design or tune for the actual per table or family settings. We set the region size differently, the block size differently. So in that order, cluster first, mostly generic, but optimized for your overall workload or overall load. And then you look at each separate use case, the tables, and do that on that level. For example, region balancer, you can actually tune that quite heavily. As a simple one, which does a balancing of regions across these servers by count. There are others who do this by a cost function. There's one who does it by pinning replicas to specific nodes. That you have to decide per use case if one of those makes sense or not. But you have to be aware that a balancer is a global feature. So if you do this cluster-wide, it may have an impact on a negative impact even on some of the use cases. So you may want to consider doing this last when you know what's happening in the cluster. You can do RPC tuning, where you can actually then split the RPC queues from single queue to split queue for reads and writes, or writes, reads and scans. And you would do this, for example, if you have lots of writes going on, and sometimes you need to read as well, and your reads are slow if you have lots of writes going on, because all your RPC handlers are busy, all your handlers do in the writes all the time, and your reads come in between. If you want to guarantee a better read performance, you could actually set aside some of the handlers only for reads. That's, again, is a cluster-wide setting, so if you do this, it may have an impact because you have fewer handlers now for writes. Is this something that you want? You can do key tuning, where you actually then play around with what I just mentioned earlier. How do you distribute the data? The key is the one that this drives the factor of how you find data in the cluster and where actually data goes. And it also drives where reads and writes are going. So key tuning will help you spread the load over all of the servers. Clever key design can really help you even out loads. That's quite interesting, because if you initially start out with a simple key, you may not get the ideal load on the cluster. And that brings us to the last part. Wrapping this up is the use cases. So placing the use cases, HBase, we used to also go into the where does it fit, and how can we have HBase? How can we do the pure throughput-oriented sort of brute force work on the other side? And Impala here, just because I was with Cloudera, so don't worry about this. It could be any other system on top of that, Hive, Tez, and LAP, or any other of these systems. Just saying there is an SQL front end over native HDFS file or HBase on the other side, and we could not really sometimes place this. We had to do like these hybrid or Lambda architectures in between. So if you look at the overall map and say, how does this fit? We have the low latency and batch on one side, and we have the random access and full scan on the other side. And you can see here sort of what plays into what. We have an option for low latency and random access, that's pure HBase, and on the right-hand side, or bottom right-hand side, we have the full scan using just brute force HDFS with MapReduce or Spark or anything like that. And if you overlay this now, oh, this is building up, okay, all right. If you're now overlaying this with use cases, HBase is good at these random reads and writes. So anything that has a simple key, like just a timestamp or like an entity, those are quite nice because you can actually find that data right away. You have to compound for other issues like hotspotting, but that's an option. You can bulk load and things like this. On the right-hand side, on the bottom, you must have something else. Like this doesn't really fit well with HBase. So HBase's access pattern being like compound key from left to right lends itself to the upper right-hand corner, and there are some areas in between where you can do some mixed workloads. You can do the like you can have time series on an entity instead of like huge time series, and you can have like sort of hybrid setups. But that is something that you have to like test carefully, tune your cluster, tune your tables, and then you should get it to work. But there might be another system that might work better. But if you have HBase anyways and you want to use those, why not? That's it. So I ran out of time, sorry. If you have any questions, I stay here for a couple of minutes. And if you have any questions, HBase, happy to answer. Thank you.